All right, we are on our heat section of this chapter. So, heat is a form of energy that's transferred between two objects. So, remember how I said that, we used some stuff from chapter 3? So, you'll see how that comes in here soon enough because we will have to do some math on this section. And some more terms. External energy is the total potential and kinetic energy of everyday sized objects, so like a pendulum or this person and this table, where internal energy is the total kinetic energy of molecular objects, so more on the atomic scale. And obviously external can be transferred to internal, which would result in a temperature increase, because if you move this table along this floor, then there's going to be some friction, which is going to cause some internal energy in those molecules. All right, heat versus temperature. So heat and temperature are not the same. Temperature is a measure of how hot or cold something is, and it's based on the average kinetic energy, where heat is based on the total internal energy. And doubling the amount at the same temperature doubles the heat. So, like for instance, if you have 1 liter of water and it's at 90 degrees, and 250 milliliters of water at 90 degrees, which one do you think would be easier to cool down? Well, probably this one, right? Because it's like a lot less. This needs 4 times the ice to cool it. So it really does matter how much there is. Okay, heating and cooling, some definitions. The definition being that it's a measure of internal energy that's been transferred from one object to another. And the way I always think about this is like if, I come from outside and it's like super cold and my hands are cold, and I come inside and I hold somebody's hand that's been inside and it's warm, how I start to feel like my hand's warming up? Well, it's not because I am, how do I say this without showing you? Normally I'm showing everyone what I'm doing with my hands in front of the room. No, it's because the heat from their hand is transferring into my cold hand. Okay, so their heat is transferring to me, not the other way around. My cold is not transferring to them, even though if somebody else came in and touched their hand, it would feel cold. Well, why? Because the heat transferred from them to me. Okay, so it's been absorbed or transferred from another object. Heating is an increase in internal energy. Cooling is a decrease in internal energy. And so you can do it by a temperature difference, where it moves from a higher temperature to a lower temperature, like the hands. And then transferring heat by doing some kind of work, like if you rub your hands together. So I could have also come in and I could have rubbed my hands together, which would have required work for me to do that. That would have burned some calories. And we could talk about calories actually in this chapter. But that actually requires me to do something in that case. Okay, measures of heat. So what I was just saying, in this chapter, we refer to energy as calories. So heat is measured in calories. And 1 calorie is what's needed to raise 1 gram of water 1 degree Celsius. Or we have kilocalories, which is 1 kilogram 1 degree Celsius. That's our metric system. If we were doing English system units, we would do BTUs instead of calories. And that's 1 pound of water, 1 degree Fahrenheit. And then you definitely need to know this conversion factor. 4.184 joules is equal to 1 calorie, or 4,184 kilojoules is equal to 1 kilocalorie. Okay? So you do need to know these conversion factors because it will, in the homework, ask you to figure either calories, kilocalories, and so on. All right, so that gets us to specific heats. Actually, there is an example before specific heat, so let me go to that really quick. Let's see here. All right, let's go on. Oh, come on. It's gonna be picky again. That's probably how you guys feel too, huh? All right, let's see here. Zoom in a little bit. So we've got example 4.4, and this is right before our specific heat section. So right about the measures of heat. This is kind of like from chapter 3 stuff. So it says a 1,000 kilogram car. Actually, I should have written it like this, huh? Gotta get that extra zero on there. 1,000 kilogram car is moving at 90 kilometers per hour. And then it tells you 25 meters per second. I might not have been that nice, okay? You might have to convert that. How many kilocalories are generated when the brake comes to a stop? So when the car comes to a stop, it's creating energy, right? It's creating a lot of friction between the tire and the concrete. So that in turn is going to cause heat. So it wants you to, when it asks you how many kilocalories, that's basically its way of saying how much heat was generated. So if something is moving, what was the equation that we used in chapter 3? We had to use kinetic energy. So remember, whenever we used kinetic energy, we had our kilograms and our velocity was always in meters per second. And I'm going to show you really quick what you would have done had it not given you that. Let's just say that it would have given you that, just in case there's one like that on the homework. All right, so let's start with our kilometers first and go to meters. So for every 1 kilometer, there's 1,000 meters. And then for every 1 hour, there's 3,600 seconds, or you could have gone from hours to minutes and then minutes to seconds. And then if you do 90 times 1,000 divided by 3,600, you would get 25 meters per second. That's where that is. All right, so now remember, because of PEMDAS, you're going to do your exponent first. So 25 times 25 times 1,000 times a half gives you, I know I've got like a ton of arrows going here. So I did all of this work and I got 312,500 joules. Remember, kinetic energy is measured in joules, but it did not ask me to find it in joules. It asked me to find it in kilocalories. So remember our conversion factors that we had on that last slide. At 4,184 joules is equal to 1 kilocalorie. This is a comma, not a decimal. So if you take 312,500 divided by 4,184, you get about 74.7-ish kilocalories. Okay? And that is basically, again, telling you how much heat is generated. Heat is measured in calories. Okay? So let me talk a little bit about specific heat, and then I'll probably have to start another video before we can get into too much more of the the heat examples, but I'm going to go back over to our PowerPoint here, talk a little bit about specific heat. So specific heat is kind of like density, where it is going to be very specific to the product. As you can see in this box, like, see this little C right here? That's the symbol for specific heat. I don't really know why, don't ask me, but that is the symbol for it. And it's measured in units of calories per gram degrees Celsius or kilocalories per kilogram degrees Celsius. Either way. So you've got specific heat for aluminum, you've got specific heat for copper, specific heat for gold. All of these different materials are going to have their own specific heat. And I think, nope, there's a table in the book, which I'll show you here in a minute, but I'll write it down here. It's table 4.2, and it's going to give you some specific heats that you will need to look at whenever you're doing your homework. Okay? So things that you have to know whenever you're solving specific heat problems, you need to know the temperature change, you need to know the mass, and you need to know what it is. And what it is going to determine what specific heat to use. So here is your equation for heat. This big Q here means heat. This is mass. This is specific heat. And this triangle T right here, that's together. That means change of temperature. All right, and I'll go ahead and write, I'll bring it up here though, so I have a little bit more space. Heat is measured in calories or kilocalories. Mass is measured in grams or kilograms. Specific heat, that's the C, is calories per gram degrees Celsius or kilocalories per kilogram degrees Celsius. And then temperature is going to be measured in Celsius. Okay, so there are some examples that are in our book, so let's go to that really quick. Just hoping that we haven't been on here too long. Oh no, what did it do? Oh, it just went to the figure. I didn't want it to do that. Oh, reading. Go to reading. There we go. All right, so let's look at example 4.5 really quick. This says, how much heat must be supplied to a 500 gram pan to raise its temperature 20 degrees Celsius to 100 degrees Celsius if the pan is made of iron or aluminum? Oops, I spelled that wrong. Just one L. Oh well. I'm a science teacher. Okay, so this is wanting us to find heat. So that's our new equation here. And so our mass that it gave us was 500 grams, and it's okay to have grams, but we need to make sure that's consistent all the way through. And what's our specific heat? Well, we have to actually look. So I said I would show you this table, 4.2, and you can see the specific heats are the same number no matter if they're calories per gram degree Celsius or kilocalories per kilogram degree Celsius. So, see, for iron, we've got 0.11. And I'm gonna do this calorie per gram degree Celsius because we used gram here. And then what is the change of temperature? It goes from 20 degrees to 100 degrees. So you just do 100 degrees minus 20 degrees, which is 80, right? So then you multiply that together. So you've got 500 times 0.11 times 80, and you get 4,400 calories. And for some reason in the book, they did 4.4 kilocalories. I don't think that it specifically said to do that. No, it doesn't. I think they were just making it a smaller number. Okay, and then you got to do it for aluminum too. So you've got 500 grams times aluminum, which is 0.22, times, again, it has a change of temperature still of 80 degrees. So you have 500 times 0.22 times 80 is going to give you 8,800 calories, or 8.8 kilocalories. Okay, so you don't really have to have as much heat when you're working with like an iron pan as you do an aluminum pan. Why? Well, I mean, if you've ever cooked with an iron skillet versus like a regular aluminum pan, they hold a lot of heat, like pretty quickly, and it gets, so it gets hot really quick and it holds it. And aluminum, it's just not as good as material. So it's going to require more heat in order to produce that change of temperature for that amount of substance. Okay, so that was example 4.5. And so I like example 4.6. Let's do it really quick. It says, what is the specific heat? So now it's wanting us to find specific heat of a 2 kilogram metal sample if 1.2 kilocalories is needed to increase 20 degrees Celsius to 40 degrees Celsius. Okay, so we're still using our same equation, but we're solving for specific heat. So you got to rearrange everything here. And I just divided mass and change of temperature to the other side. So my heat is 1.12, or no, I don't even know where I got that. Not 1.12, it's just 1.2. Divided by the mass, which is 2 kilograms, divided by the change of temperature, which is 20 degrees Celsius. So let's see here. I got 1.2 divided by 2 times 20. So I end up with 0.03 kilocalories per kilogram degrees Celsius. Okay, so you might not always have to solve for heat. You might have to solve for specific heat or mass or even the change of temperature. But you do want to make sure that your units are the same. So if it would have given kilocalories and grams, you would have wanted to converted one of those to either calories or, kilograms. All right, so I'm going to stop the video.